Hello everybody. In this video, we are going to review conditional probability and independence on problems. This is problem number 1. Suppose that A and B are two events for which probability of A is 0.26 and probability of B is 0.68 and probability of A and B is 0.33. Find the probability A given B. We're going to start with the definition of the conditional probability. Probability of A given B by definition is their intersection over the probability of the given condition. Here the given condition is always written in the second position. Here we were given their intersection explicitly, 0.33, and we were also given the probability of B, 0.68. So for this problem, all you have to do is just to substitute on the definition. So the answer is 0.33 over 0.68. Problem number 2. Suppose that A and B are two independent events for which probability of A is 0.25 and probability of B is 0.78. Find each of the following. Probability of A given B. Again, by definition, probability of A given B is equal to their intersection over the given condition probability of B. We were given a piece of information that they are two independent events. By the definition of independency, the intersection of A and B is their product if they are independent. So their intersection will be their product, which will be 0.25 times 0.78 all over probability of B, which is 0.78. And actually here you can see that probability of A given B is probability of A if they are independent. So similarly, probability of B given A is probability of B because we know that they are independent. So you can substitute the values from above. Probability of A and B is their intersection. So their intersection is their product because they are independent. So it's going to be probability of A times probability of B, which is 0.25 times 0.78. And probability of A or B, in general, the union by definition is probability of A plus probability of B minus their intersection, because we don't want to overcount. So probability of A is 0.25, probability of B is 0.78, and their intersection is 0.25 times 0.78. So whatever the value here will be the answer here. Or you can directly write down this. Problem number 3. Suppose that A and B are two events for which probability of A is 0.24, probability of B is 0.81, and probability of B given A is 0.39. Find each of the following. We were asked to find A and B, so we will start from the definition of the conditional probability. Probability of B given A is their intersection, probability of A intersect B or B intersect A, same thing, over probability of A. Here we were given probability of B given A, which is 0.39, and that's what we're solving for, A intersect B, and probability of A is given 0.24. if you solve for this unknown in this equation, it's going to be cross multiplication. So 0.24 times 0.39 is the answer. Probability of A or B. Probability of A or B is A union B, which is probability of A plus probability of B minus their intersection. We know probability of A, 0.24. We know probability of B, which is 0.81. And we have just solved their intersection. 0.39 times 0.24. So this whole line is the answer here. Probability of A given B. Probability of A given B, let's write out the definition, their intersection over given condition. Their intersection, as we found, 0.39 times 0.24, and probability of B is 0.81. So this whole fraction is answer here. Problem number 4. A firm has classified its customers in two ways, according to whether the account is overdue and whether the account is new, less than 12 months, or old. An analysis of the firm's records provided the input for the following table of joint probabilities. So we were given contingency table. This is called contingency table or two-way frequency table. Now we're going to extend this table and write the totals. So we're going to sum vertically and horizontally. So the total new is 0.07 plus 0.11, which is 0.18 here. And if we add them up, 0.48 plus 0.34, we get 0.82. And if we add vertically, we get 0.55 here, and we get 0.45 here. And always the corner here, right bottom corner, is always 1, which is representing the 100% of whole sample space. Now our interpretation will be like this. The total probability of the overdue is 55%. The total probability of new is 18%. Likewise. Now part A is asking if the account is overdue, what is the probability that is new? So that is the way to ask probability of new given overdue, which is their intersection over given condition. Their intersection is in the table here. New and overdue is 0.07, and the total probability of overdue is 0.55. So this is the answer for the first part. The second question is asking if the account is new, what is the probability that it is overdue? So this time, probability that it is overdue given it is new. Again, their intersection over probability of new. Their intersection is 0.07, and the probability that it is new is 0.18. So 0.07 divided by 0.18 is the answer. Problem number 5. 100 people were surveyed, and one question pertained to their educational background. The results of this question and their genders are given in the following table. So we were given the table, contingency table, in numbers, not in probability. We have to be careful about it. But here, the good news is the total is 100, so we can consider it as probability, like 0.29, 0.15, 0.44, 0.21, likewise. If that number was not 100, then we had to convert it into percentage. So question number 1. The person is female or has a college degree. So probability of the person is female or college degree. So that is probability of female plus probability of college minus their intersection by the definition of union. So probability of female is 44. Probability of college is 0.50 minus their intersection. Female and college, their intersection is here, 0.29. So the answer is 0.44 plus 0.5 minus 0.29. This is 29. Question number 2 is asking male or does not have a college degree. So we will go to same logic. The male, total male is 56%. Who does not have college degree, total is 50%. And their intersection is male, no college, 0.35. The person is female or does not have a college degree. The person is female is 44%. 44%. And does not have college degree is 50%. And their intersection, female, no college degree, is here 0.15. So this is the answer. Problem number 6. In a recent election, there were 1,000 eligible voters. They were asked to vote on 2 issues, A and B. The results were as follows. 250 people voted for A, 550 people voted for B, and 75 people voted for A and B. If one person is chosen at random from the 1,000 eligible voters, find the following probabilities. If one person is chosen at random from the 1,000 eligible voters, find the following probabilities. So here let's write out people who voted for A is 250 people, for B is 550 people, and A and B together is 75 people. Now the person voted for A given that he voted for B. So probability of A given B. The person voted for A given that he voted for B is the same as the conditional probability of A given B. So their intersection over probability of given condition. So A intersect B is 75 over 1,000. Out of 1,000 people, 75 of them voted for A and B at the same time, so that is the percent. So probability of B is 550 over 1,000. So this is the answer. So it's gonna be 75 over 550. So the second part, this time probability of B given A. Again, their intersection over given condition. Their intersection is 75 over 1,000, and 250 people voted for opinion A, so it's going to be 75 over 250. Or you can write out whole fraction. Problem number 7. A bag contains 5 red marbles and 6 white marbles. 2 marbles are drawn in succession without replacement. Find the probabilities of the following events. 1. First marble drawn is red and the second is white. So let's write out. We have 5 red and 6 white. Total we have 11 marbles. So we have 2 coordinates. For the first coordinate we are picking up red. So it is 5 over 11 chance times, for the second coordinate we are picking up white, this time our denominator will be 10 because we are not putting the marble back. Now we have 10 marbles and we have 6 white, so 6 out of 10. So 511 times 610 is the answer. In the second condition, both marbles are drawn red. So we have again two coordinates. For the first coordinate, we are picking the first red, which is 5/11, times for the second, we are picking another red, which is 4/10. This time we have 4 marbles left and 10 total. So 5/11 times 4/10. Problem number 8. A family has 3 children. Assume that each child is as likely to be a boy or it is to be a girl. Find the probability that the family has 3 girls if it is known the family has at least 1 girl. So this question is looking like conditional probability. What is the probability of 3 girls given that at least one of them is girl? If we approach this question this way, the answer will be wrong. We're going to do extraordinary approach for this question. But first, let's see why conditional probability will be wrong for this. Our sample space is omega is this. And we have total 8 options here. And by the definition of conditional probability, their intersection over the conditional or the given condition we see this intersection 3 girls and at least 1 is girl is 1/8, and at least 1 is girl is 7/8, and we obtain 1/7, and this is wrong. So here, instead of this, we're going to approach this question this way. What we are calculating is probability of 3 girls. And we know that one of them is girl, 100%, we are sure about it. And that can be either in this order. The first one can be girl. The second one can be girl. Or third one can be girl. In either condition, we have 2 coordinates empty. So our new sample space, which is, let's call it omega hat, will be, so the first one is boy, then the second one is boy, or first one is boy, second one is girl, or first one is girl, second one is boy, or they are both girls. So this is our new sample space. And the only condition that gives us 3 girls is picking up girl-girl option. And in the new sample space, girl-girl option is only 1/4. And only this condition provides us 3 girls. So the answer here is 1/4. Problem number 9. What is the probability that at least one of a pair of fair dice lands on 4, given that the sum of the dice is 6? Here we are going to compute the probability of at least one pair is one of a pair lands on 4, given that sum is 6. Here our omega, the sample space, is the tuples of 2 starting from 1, 1 through 6, 6. So we have 36 in total. And this event be A, and let this event be B. So event A is the at least one pair lands on 4. So that is 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 4, or 4, 1, 4, 2, 4, 3, 4, 4, we don't need to repeat it, 4, 5, and 4, 6. So let's take out the repeated. And our event B is sum of 6. Sum of 6 is either 1, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. So here we have 5 out of 36 options. Here we have 11 out of 36 options. Now let's go to definition of conditional probability. Their intersection over the probability of given condition. Probability of given condition is 5 out of 36, which is probability of P. Their intersection is whatever is common here. So it's gonna be at least one of them will be 4, and their sum will be 6. So we have only 2 out of 36 options. So 2 divided by 36 over 5 divided by 36 is the answer, which is 2/5. 2/5 is the answer. Problem number 10. In a certain community, 16% of the families own a dog, and 25% of the families that own a dog also own a cat. It is also known that 29% of all the families own a cat. So using this information, what is the probability that randomly selected family owns both dog and a cat? Let's start with part 1, but before that, let's rewrite the information given, either using 3 branches or Venn diagram. So families who own dog, families who own cat, and none. So we were given the information that 16% of the families own dog and 29% of the families own cat, so 55% own none. And we were also given information that 25% of the families who own dog also own a cat. So we know that 1/4 of the dog owners also own a cat. Okay, so question 1 is asking probability that a randomly selected family owns both dog and a cat. So it is the product of this. (0.16 times 0.25). So we obtain here 0.04. Let me also show this in the Venn diagram. So our sample space is this, dog owners and cat owners. So this is our omega sample space, dog owners, cat owners. We know that 16% dog owners and 0.04% is 4% is both owning dog and cat, so this is 12%. Out of 29%, 4% is here, so 25% is here, and 55% is out. So you can also see here in the Venn diagram that they both own dog and cat is 0.4. Because here total dog owners has to be 16%. 0.12 plus 0.4 is 16%. Okay, second part of the question is asking what is the conditional probability that randomly selected family owns a dog given that it doesn't own a cat? So it doesn't own a cat, so the complement of cat. So this is, by the definition of conditional probability, is their intersection. That's gonna be the intersection of D and C naught over probability of C naught. And if we expand this formula, probability of D intersection C naught means probability of D minus probability of D and C. So this numerator is equal to this numerator, and probability of C naught is 1 minus probability of C by the complement. So we know that probability of dog is 0.16. We know that their intersection is 0.404, and we know that this is 1 minus 0.29. So the answer is 0.169. Problem number 11. A sample space contains 6 sample points and events A, B, and C as shown in the Venn diagram. The probabilities of the sample points are given from P1 to P6. Using the Venn diagram, we're going to compute these conditions. Probability of C naught is the probability of 1 plus probability of 2 plus probability of 3 plus probability of 4, because it is outside of C, and if you put the values given above, you're going to obtain 0.8. In part B, we are going to compute probability of C given B, and by definition it's their intersection over the probability of given condition, and their intersection here is probability B and C is probability of 5, and probability of B is represented by P3, P4, and P5. So if you substitute the values given above, you're going to get 0.1 over 0.45. So 0.1 over 0.45 here, and this is 0.8. Part C is asking probability of C naught given A, which is probability of C naught intersect A over probability of A. You can either here substitute C naught intersect A. C naught is everything else but C, which is 1, 2, 3, 4, and intersected with A, you obtain 1, 2, 3. Probability of 1 plus probability of 2 plus probability of 3, or you can say probability of A, what you get, over probability of A is 1. So exact same value on top and bottom, you obtain 1. Problem number 12. A box contains 1 yellow, 2 red, and 3 green balls. 2 balls are randomly chosen without replacement. Define the following events. Events are given A, B, C, D, and we're going to compute these conditions. Our box contains 1 yellow, 2 red, and 3 green balls. And in condition 1A, we are computing probability of A given B. By definition of conditional probability, this is their intersection over the given condition. Now let's handle probability of B and probability of A intersect B. Probability of B, here the definition of the event says at least 1 ball is red. At least 1 ball is red means 1 minus no ball is red. So we can approach this by the complement. So it's going to be 1 minus no ball is red. So we are picking 2 balls in tuples of 2 coordinate. So here we want no red, which is going to be 4 out of 6 times, and the second ball we don't want red again, so it's going to be 3 out of 5 because without replacement. So if you compute 1 minus this fraction, it's going to be 1 minus 2/5, which is 3/5. So we know the probability of B. Now let's compute probability of A intersect B. A intersect B says at least 1 ball is red and 1 of the ball is yellow. We need to consider A intersect B like the event that 1 ball is yellow and at least 1 ball is red. For this to happen, we either pick a red ball first and then yellow, or we first pick yellow and then red ball. So it's going to be either this or that. We either pick up red and then yellow, or yellow and then red. So picking here red is 1/3, which is 2/6, times picking here yellow, we have only one option, 1, but out of 5, because without replacement. And here picking yellow ball is 1 out of 6, and picking here red is 2/5. We have 2 reds and 5 marbles left. If you do this calculation, you obtain 2/15. And now we can place it. 2/15 over, you can express it as 9/15 over 9/15. So you obtain 2/9. Okay, let's go to part B. So I'm going to clean up part A so we can compute part B. In part B, we are computing probability of D given B. We already computed probability of B in the previous part. It was 9/15. Let's keep it here. And probability of D intersect B over probability of B will be the answer. We know that this is 9/15. So probability D intersect B is both balls are of the same color and at least one of them is red. So we have only one option, red, red, because we want one of them red and 2 of them are the same colors. So this is the only condition. So probability of D intersect B is equal to red, red. And how can we pick up red, red? At the first coordinate, we can pick 2 out of 6. And at the second, we pick 1/5. So this is going to be 1/15. And 1/15 over 9/15 is 1/9. So 1/9 is the answer here. Let's go part C. So let me clean up part B. In part C, we are computing probability of D given C0, which is their intersection, over probability of C0. Probability of C0 is 1 minus probability of C. And probability of C, both balls are green. So to be able to get both balls are green, we need the first pick up 3 out of 6 times 2 out of 5. This is going to be 1/5. So 1 minus 1/5 will be C0, which is going to be 4 over 5. So now we know that this is 4 over 5. Now we're going to compute D intersect C naught. D intersect C naught. C is both poles are green. C naught is both poles are not green. And at the same time, they are the same color. Again, we're pointing out only red. So their intersection is again red. We want both same color and we don't want them to be green, which means we want red. We already computed it in the previous part. It's 1/15. So here 1/15 over 4 over 5, we can express it as 12 over 15. So the answer will be 1/12. Problem number 14. You ask a neighbor to water a sickly plant while you're on vacation. Without water, the plant will die with probability 85%. With water, it will die with probability 50%. You are 89% certain the neighbor will remember to water the plant. When you're on vacation, find the probability that the plant will die. Let's make tree branch. So we know that 85% sure that the plant will die without water, and we know that the plant will die with 50%, and we're sure that the neighbor will remember 89%. So the remainder, we are sure that the neighbor will forget 11. So we're calculating here probability that the plant is dead by the Bayes theorem. Probability that plant is dead given watered times watered. This is the different version of Bayes theorem. Probability that the plant is dead forget times probability of forget in words. In application, multiplication of this plus multiplication of that. So 0.85 times 0.11 plus 0.5 times 0.89. This is the answer. In part B, what is the probability that the neighbor forgot to water it? So it's going to be this 0.85 times 0.11, because that's the forgot without water, all over everything. 0.85 times 0.11 plus 0.89 times 0.5. So this answer will be here. Problem number 15. Two marbles are drawn randomly, one after the other, without replacement, from a jar that contains 5 red marbles, 7 white marbles, and 2 yellow marbles. Find the probability of the following events. First of all, we have a box that contains 5 red, 7 white, 2 yellow, total 14, and without replacement. Now we're going to calculate picking up red marble and then white marble. Picking up red marble is 5 out of 14, and then picking red and after that white marble is 7 out of 13. So this is the answer. 5 over 14 times 7 over 13. In part B, we are picking white marble and then another white marble. The first white marble is 7 out of 14 and the second white marble is 6 out of 13. 7 over 14 times 6 out of 13. In part C, we are picking 2 marbles and none of them are yellow. So here we are picking non-yellow, which is 12 out of 14, and again non-yellow, which is 11 out of 13. So this is the answer. Question number 16. Consider the experiment where a fair coin is tossed. If the toss results in a head, then 1 die is thrown. If the toss results in a tail, then 2 dice are thrown. Let x denote the random variable that counts the number of spots showing on the thrown die or dice. The range of the values that x can assume are the positive integers from 1 to 12 inclusive. So according to this information, we are going to compute the probability that x can take the value 1 through 12. Before that, let's try to understand the question in this diagram. First, we are throwing a coin. It is either head or tail, which is 50% chance one of them. If it is head, then we are throwing a die, and whatever the number comes on top is the value of x. This is the value that x can take 3. If it is tail, then we are throwing 2 dice. And this time we are adding the numbers on top. So that's the value that x can take. Now we understand the question, so let's go ahead and write out that x can take value 1. There is only one condition. We have to throw head and the die has to be 1. And taking head is 1/2% chance, and getting 1 in 1 die is 1/6% chance. So this is 1/12. For x to take 2, we have option either head and 2, or we throw tail and 1/1. So h2 is 1/2 times 1/6, and tail is 1/2, and getting 1 is 1/6 and 1/6. So that is the probability of x equals to 2. For x equals to 3, we have h3 or tail 1, 2 or tail 2, 1. For x equals to be 4, we have to throw h4 or tail 1, 3 or tail 2, 2 or tail 3, 1. For x to be 5, we have to throw h5, t1, 4, t2, 3, t3, 2 or t4, 1. For x to be 6, we need h6 or tail 1, 5 or tail 2, 4 or tail 3, 3 or tail 4, 2 or tail 5, 1. For x to be 7, we need tail 1, 6, tail 2, 5, tail 3, 4, tail 4, 3, tail 5, 2 and tail 6, 1. Let's continue with the value that x can take is 8. So that x is equal to 8 is we need tail 2 6, we need tail 3 5, we need tail 4 4, we need tail 5 3, and we need tail 6 2. And for x to be 9, we need tail 3 6, tail 4 5, we need tail 5 4, and we need tail 6 3. For x to be 10, we need tail 4 6, we need tail 5 5, and we need tail 6 4. And for x to be 11, we need tail 5 6, and we need tail 6 5. And finally, for x to be 11, we need only tail 6 6, no other option. And again, let me do sample calculation. For tail we need 1/2, for getting 6 is 1/6, and for 6 another getting 1/6. So that's going to be the answer for the value that x takes 12. So further, find the probability that x is divisible by 5. Divisible by 5, we need the probability of that x equals to 5 plus that probability that x equals to 10, because those are the only two numbers that are divisible by 5. So whatever value you have written here plus whatever value you have written here will be here added. Problem number 17. Factories A and B produce computers. Factory A produces 4 times as many computers as factory B. Probability that an item produced by factory A is defective is 0.02, and the probability that an item produced by factory B is defective is 0.043. A computer is selected at random and it is found to be defective. What is the probability it came from factory A? Let's make the 3 branches. This is the base theorem question. So this is factory A, this is factory B. We know that factory A is producing 4 times as many computers as B, so let B be x, so this is going to be 4x. We know that together they have to be equal to 1, so 4x plus x is equal to 1, then here x is equal to 1/5. So instead of x we can write here 1/5 or 0.2, and for 4x here we can write 4/5 or 0.8. So this is 0.8, this is 0.2. And we know that factory A is making 0.02 or 2% defective items. Let's denote it with negative sign. And for the correct computer, that's denoted with positive sign. And 98% correct item. And here likewise 0.043 defective item and 0.957 is the correct item. So this is the complementary of defective item. So this is the complementary of the defective item. Now what we are calculating is probability that the computer is produced in factory A, knowing that it is defective. So it is going to be 0.02 times 0.8 all over everything. It's going to be this 0.08 times 0.02, this is times all over 0.8 times 0.02 plus, since we are picking the defective one, so the same group we have to pick up, so it's going to be 0.2 times 0.043. So this fraction is the answer. Problem 18. If the knowledge that an event A has occurred implies that a second event B cannot occur, then the events A and B are said to be disjoint. So this is the definition of disjoint. You cannot be at home and at the school at the same time. It cannot be it is raining and it is not raining at the same time. And if event A and B are as above, if they are disjoint, and A has the probability of O2, B has the probability of O3, then what is A union B? If two events are disjoint, then their union is probability of A plus probability of B. Union is 0. Because their intersection is 0. So this is going to be 0.2 plus 0.3. Problem 19. If the letters in the word poker are rearranged, what is the probability that the word will begin with the letter E and end with the letter R? So we have 5. So we have 5 coordinates. And we would like first letter to be E and the last letter to be R. And we don't mind what it is in here, this combination. We know that total we have 5 factorial combination letters, which is 120 words we can produce using these letters. But we wanted to start with E, so we have 1/5 chance to pick E here at the first coordinate. 1 out of 5 times, likewise we need this time 1 out of 4 combination, 1 out of 4 probability to pick R here, because 4 letters left and we want one of them to be here. So it's going to be 1/20, 0.05 chance to get a word starting with E and ending with R. Problem number 20. If A and B are mutually exclusive events with probability of A is 70%, then probability of B, we know that they are mutually exclusive, so their sum has to be 100%, so probability B cannot exceed 30%. If probability of A is 20% and probability of B is 30% and their intersection is 0.06, then A and B are independent, because if two events are independent, their intersection is their product. And if you multiply 0.20 times 0.30, you obtain 0.06. Problem 21. In a large city, 37% of all restaurants accept both Master and Visa cards, and 50% accept MasterCards and 60% accept Visa cards. A tourist visiting the city picks at random a restaurant at which to have lunch. Define the following events. M is representing the Master credit cards and V is representing the Visa credit cards accepted. Let's try to make the Venn diagram. So in the Venn diagram we have MasterCard and we have Visa card. And we know that 37% accept both, 0.37, and we know that 50% accept MasterCards only. So this is going to be, remaining is 13 plus 37 is together 50%, and this is going to be 0.23 plus 37 is 60% together for the Visa card. And the rest is, this is altogether is 73%, so the rest is 0.27%. Now our sample space is ready. Are M and V are disjoint? No, they are not disjoint, because if they were disjoint, their intersection had to be 0. Are they independent? They are not independent, because if we multiply probability of m times probability of v, we don't get their intersection. Is m complement of v? No. Complement of v is everything else, including 0.27 and this. If events m and v are independent, which of the following would be true? If two events are independent, then probability of v given m is probability of v, m given v is probability of m, and their intersection is their product. The rest is wrong. What is the probability that a given restaurant does not accept Master or Visa credit cards? Already here in the Venn diagram, 0.27. Problem number 22. For two events A and B, probability of A is 0.6, probability of B is 0.2, and we were given that A and B are independent. Then what is the probability of A given B? By definition, we know that probability of A given B is their intersection over the probability of given condition. We know B, which is 0.2 given. Their intersection, we know that they are independent, so their intersection is their product. Probability of A intersect B is probability of A times probability of B. So the top will be 0.2 times 0.6. And actually we know that probability of A given B is probability of A if they are independent. Their union, probability of A union B, will be probability of A plus probability of B minus their intersection, A intersect B. Here we know A is 0.6, we know B is 0.2, we know their intersection is 0.2 times 0.6. So this everything is answer here. Probability A intersect B, as we said above, product, their product. Part B, if A and B are dependent and probability of A given B is 0.7, then their intersection. Okay, we're gonna start with the definition of conditional probability, which is going to be their intersection over given condition, here B, and we're solving for their intersection. We know probability of B is 0.2, and 0.2 times 0.7, if we cross multiply, we solve for their intersection. So 0.2 times 0.7. Probability B given A, likewise, their intersection over probability of A. We know probability of A is 0.6. We have just solved their intersection above, 0.2 times 0.7. So this fraction is the answer. 0.2 times 0.7 over 0.6. Problem number 23. Consider the experiment where a pair of fair dice is thrown. Let x denote the random variable whose value is determined by multiplying the numbers of spots showing on one die by the number of spots showing on the other. The range of values that x can assume are the positive integers. Now we're going to calculate the probability that x can take the value 1, 2, through 36. Let's try to understand the question. We are throwing two dice. We are checking what numbers are on top, and we are multiplying it. We take the product of those two numbers, which is 6. So that's the value that x can take 6. Now let's write out the value that x can take 1. We have only one condition, 1, 1. For x to take 2, we can get either 1, 2 or 2, 1. For 3, 1, 3 or 3, 1. For 4, 1, 4 or 4, 1. For 5, 1, 5 or 5, 1. And for 6, 1, 6, 6, 1, 2, 3 or 3, 2. For 9, for 8, 2, 4 or 4, 2. For x to take 9, we have one option. For x to take 10, we have either 2 times 5 or 5 times 2. For 12, 2 times 6, 6 times 2, 3 times 4, 4 times 3. For 15, 3 times 5 or 5 times 3. So likewise we go up to 36, which is only one option, 6 times 6. Now let's see how we calculate the probability. For the first die to get 1 is 1/6. For the second die to get 1 is 1/6. So 1 out of 36 is the answer here. Let's do, for the second one we have to add this. So 1/6 times 1/6 plus 1/6 times 1/6. So it's going to be 2 out of 36. Let's do this sample calculation. This plus this plus this. So 1 over 36 plus 1 over 36 plus 1 over 36 plus 1 over 36, 4 out of 36 for 12. Part B, find the probability that x is divisible by 18. Divisible by 18, we need only two values of x. Probability of 18 plus that x is equal to 36, because those are the only two numbers that are divisible by 18. So whatever value you find here plus whatever value you find here will be added. So that's it for this conditional probability and independence review.